Hey everyone, welcome back. We are to chapter 8, hypothesis testing. This is a huge deal. This is the beginning of giving you the tools so that you can investigate if something is real or not real, which in this day and age is very, very important to know how to do. So we're going to start with something called hypothesis testing. And we're going to introduce, what I'm going to do is I'm going to go through all the elements of hypothesis testing. And then in the next videos, we'll actually do hypothesis testing. Um, so here we go. Let's get started. In statistics and hypothesis is a claim or a statement about a property of a population. Now, this is the mean, the proportion, standard deviation, or variance are the four things that we're going to investigate. In fact, there's 5 sections to this. The first one is an introduction to hypothesis testing. And the next section is on the mean. The next one's on proportion. Next one's on standard deviation and variance. So let's start at the beginning. We're going to use a claim to create a null hypothesis and an alternative hypothesis. The null hypothesis is denoted H sub 0. And this is a statement that a value in a population parameter is equal to some claim value. Alternative hypothesis, which is H sub 1, is what I'm going to use. Other courses or subjects could use H sub A for alternative. It's a statement that a parameter has a value that somehow differs from the null hypothesis. So the symbols we'll be using for this are not equal to, greater than, or less than. And which one we use will depend on what the actual statement is. So let's dig out our null and alternative hypothesis for this example. A recent study at a university showed that the proportion, so we're talking about a proportion, of students who commute more than 15 miles to school is 20%. Suppose we have good reason to suspect that the proportion is greater than 20%, and we carry out a hypothesis test. All right, so here we go. We have H naught, which is that the proportion is equal to 20%. So the null hypothesis is always equals. You can see I put that up there, equals. The alternative is something other than equals. In this case, it says that it's greater than 20%. So here's our null and alternative hypothesis for this statement. Next one, a car leasing firm's records indicate that the mean number of miles, now we're talking about mean, number of miles driven annually in its cars has been about 14,500 miles. The firm suspects that this number has decreased this past year. All right, so let's do our null hypothesis. We're now testing the mean. And they think that the mean is equal to 14,500 miles. The alternative hypothesis is that it has gone down. So they say that it has decreased. So mu is now less than 14,500. That's it. That's all we're doing right now is we're just trying to identify what is it that we're actually testing. Typically, the claim is going to be the alternative hypothesis. And typically, that's what we're testing. All right. The breaking strengths of cables produced by a certain company are approximately normally distributed. The company announced that the mean breaking strength in pounds is 2,160 pounds with a variance of 35,344. A consumer protection agency claims that the actual variance is higher. So we are testing the variance in this case. And variance is sigma squared. And they think 35,344. And the Consumer Protection Agency thinks that that is actually higher. All right. The records of a casualty insurance company show that in the past, its clients have had a mean of 1.7 auto accidents per day with a standard deviation of 0.04. The actuaries of the company claim that the standard deviation of the number of accidents per day is no longer equal to that. So here we go. So we are testing the standard deviation in this case. The alternative, it doesn't say more or less, it just says they don't think that it's that anymore. There it is. All right, and next up, we're going to find the level of significance. Typically, our levels of significance are alpha is 10%, alpha is 5%, or alpha is 1%. Now, it doesn't have to be these. It can certainly be something other than that. And typically, with your homework and exams and everything like that, that will be given to you, so you won't have to select that. But in real life, of course, you'll need to decide what level you want to test it at. All right, next up, we're going to find what's called the test statistic. The test statistic. And the formulas for finding those are right here on the right. So you see z equals, t equals, z equals, and chi-squared equals. Now, the good news is, even though right now we are going to use these formulas, when we actually do hypothesis testing, most of these are already built into the calculator, and it will do all of this for us. All of them except the standard deviation or variance, that the chi-squared that you see down there, that n minus 1 times s squared divided by sigma squared, that one we're going to have to manually do. But right now we're going to manually do all of these. And here we go. So we're going to find the test statistic. The claim, 3/4 of all adults believe that it is important to be involved in their communities. 3/4 is a proportion. And 3/4 is actually 0.75, right? 3 divided by 4, 0.75. Based on a poll of 1,021 randomly selected adults, 89% believe it is important to be involved in their communities. All right, now they don't say one way or the other whether it's equal to or not equal to, so our default will be not equal to. And they tell us that n is 1,021. P hat is 0.89. And our formula, let's see if I can squeeze that in there, up top there is going to be, I'll use purple. Is here, and to be clear, Q hat, not Q hat, we don't need Q hat, we need Q. Q, so let's write that over here. Q is 1 minus 0.75, 0.25. All right, so here we go. So P hat, 0.89, minus P, which is 0.75, divided by the square root. 0.75 is P, Q.25 over N, which is the 1,021. Now we have to be really careful how we put this into our calculator. The numerator I'm going to put in parentheses. And I'm not going to use parentheses under the radical. That can really mess you up with your calculator depending if you know how to use your calculator correctly or not. And what I mean by that is every calculator will let you or will not. So they kind of, each one kind of has their own set of rules here. So our test statistic is 10.3301. Actually, 10. I said that wrong. 10. There we go. Now, right now, we're just learning how to do each of these things. We don't know what to do with these numbers yet. We will eventually, but certainly by the end of this chapter, we will definitely know what to do with those. Part B. For adult females, the standard deviation of their white blood cell counts is greater than 5. Okay, so our null hypothesis, standard deviation is 5. The alternative, sigma, is greater than 5. The random sample of 40 adult females has white blood cell counts with a standard deviation of 2.28. So this is telling us that N is 40. Let's stay consistent with the colors. So N in this case is 40. S in this case is the 2.28. That is the standard deviation of the sample. And our formula for test statistic is here. All right, so N minus 1 is 39. S is 2.28 squared over sigma squared, which is 5 squared. Let's see what we get. I'm getting 8.1095. All right, I hope you're keeping up. We have a few more to go. Claim for adult females, the mean of their white blood cell count is less than 8. So our null hypothesis, the mean is equal to 8. The alternative hypothesis is that the mean is less than 8. The random sample, so let's write out what we have. We have N is 40, X bar, 7.15. The sample standard deviation is 2.28. And our formula is going to be T. Now let's talk about a T distribution for a minute. How do I know if I'm using a T distribution or I'm using a Z distribution? So that's the difference between the first mean one and the second mean one that you see there, the T and the Z. And here is the big deal. And this is not going to be that easy at the beginning for you to identify just because it's new for you. Is the population standard deviation known? If it's not known, we're going to use the T distribution. If it is known, then we're going to use the Z distribution. And how do we know which one it is? Because all of the problems are going to have a sample standard deviation. So how do we know if we're talking the population or the sample? So it says for adult females, the mean of their white blood cell counts is less than 8. Now it starts talking about a sample. So everything after this is going to be referring to this sample. A random sample of 40 adult females has a white blood cell counts with a mean, so that's the sample mean, 7.15, standard deviation of 2.28. So you'll notice we don't have anything about the population standard deviation. So this is going to be sigma is not known. This is going to be a T distribution. Damn it. Which means I'm going to be using the formula T equals, and it's going to be that one right there, X bar minus mu. Yeah, over capital S over root N. So X bar minus mu over S divided by root N. And here we go. Let's see, X bar is 7.15. minus mu, which is 8. So this is going to be a negative test statistic. S is the 2.28 divided by root 40. Now, there's a lot of weirdness with this particular formula that we're going to have to be extra careful on. So I'm going to go parentheses 7.15 minus 8, close parenthesis, divided by, and I'm going to use parentheses again, just because it's weird fraction in there. So 2.28 divided by the square root of 40. So I'm getting about negative 2.3578. Oh, I didn't do it in purple like I did the other ones. That's okay. And so we know how to find our test statistics now. But like I said, except for the chi-squared, all of these will automatically be calculated for us. So thank you, calculator person. You're amazing. All right. Let's keep going. The test statistic alone is not enough to give us enough information to make a decision about the claim being tested. For that decision, we have two ways of checking it, and I'm going to do both methods every time, just so we can see that they're always in sync with one another. We can use either the p-value method or the critical value method. And like I said, every time I'm going to do both methods. So it kind of becomes a blur. So both things should be confirmed every time. So we're going to talk about finding the critical region. I'm going to color code this. My critical regions are always this is your alpha. And some homework don't call it the critical region, they call it the rejection region. So I may call it the rejection region, but it means the critical region. The critical region is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. A two-tailed test means that the alternative hypothesis is a not equal to. A left-tailed test is when the alternative hypothesis is a less than. And a right-tailed test is going to be when the alternative hypothesis is a greater than. So I'm going to do some drawings here to give us just an idea of what we're going to be looking at. All right, we will start with a graph. All right, so I'm going to assume this is a z distribution. It could be a t distribution, could be chi-squared. All the same logic is going to hold. And I'm assuming this is a right-tail test, just to so it's a greater than. And what I'm going to do is I'm going to call this the p-value. It's the area under the curve. And this down here is your test statistic. So we just found a bunch of test statistics. Negative 2.3578, 8.1095, 10.3310, and so on. So that's our test statistic, and it's the area to the left or right of the test statistic. Now, stop. Sorry, my computer's acting really weird right now. Stop that. Okay. Here, this is the rejection region, or the critical region. our alpha. And this is the critical value. Now, in this case, I'm going to note that the p-value is definitely bigger than, meaning the blue area is more than the red area, the rejection region. Which is, of course, our alpha. And the other side of that, over here, we have Z. And I'm going to say that we're going to have the same critical value. And again, this is our rejection region. Now we're going to be here. This is our test statistic. And this area right here is our p-value. And in this case, we can see that the p-value is less than rejection region. Again, that's our alpha. And this is what we're going to be looking at. The one is bigger than or less than the other. And that, in a minute, we'll see the significance of what that's going to mean for us. Also, I want to point out that my critical value, my test statistic in the left one is not in the rejection region. However, my test statistic in the right one is in the rejection region. So we're starting to get more and more bits and pieces. All right, let's keep going. Use the given statement to find the p-values. The test statistic of z equals 2 is obtained when obtaining a claim that p is bigger than 0.5. Okay, so my null hypothesis is that p is 0.5. My alternative hypothesis is that p is bigger than 0.5. First of all, that means that it's going to be left-tailed. So greater than means that it's left-tailed. This is it. They say it's Z. There's 0 here. And they say the test statistic is 2. That's way over here. That's really far away. And because it's greater than, it's a right tail. So to find the area from 2 to infinity, I'm going to need to use normal CDF. We're starting at 2, and we're going on to infinity. And because it's standard normal, I don't need to put the mean in the standard deviation. So second vars, which is my distributions, normal CDF, 2, comma, infinity. So this is about 0.0228. And that is that area right there. My p-value. And as expected, it's quite small. That's 2 standard deviations away. All right, let's keep going. So let's grab our graph here. There we go. And this one says that our null hypothesis is that p is equal to 0.6. Our alternative hypothesis is that p is bigger than 0.6. Once again, that's 0 there. This is a z distribution. This time we're way over here at -3. So it's way over here at -3. And the p-value here is going to go from normal CDF -infinity to -3. Let's see what we get. It's going to be a really tiny number, yeah. That's pretty darn close to 0. There's our p-value. All right, now we have a not equal to, so this is a bit of a game changer. So let's get our graph. All right, again, this is Z, our null hypothesis, 0.25. Our alternative, P is not equal to 0.25. Now, if you remember, the not equal to means that it is a two-tail. And what they are giving us is Z equals -1.23. And to be clear, this area here is only half the picture. So this is only 1/2 the p-value. The other half is over here. So to find the p-value, I'm actually going to find that half a p-value. Which is going to be normal CDF -infinity to -1.23. And again, that's only going to be half of my p-value. This is about 0.1093. So 0.1093. So to get the full p-value, I'm going to go 0.1093 times 2. Now, once again, we will have to use this logic eventually. But for right now, when we're doing our tests, the calculator will automatically double it for us and all that kind of stuff. But we are going to hit a point where we are going to have to manually do it like this. All right. Let's keep going. I'm having so much trouble with this. All right. Next up, we have the critical value method. And I'm going to go ahead and draw it again. Here. All right. So and here is going to be our alpha. And here is our test statistic. And remember, for our alpha, we can find the critical value. using inverse norm. And I'm going to so once again, I'm at 0. And in this case, our critical region is going to be the same. But this time, our test statistic is going to be in the rejection region. So these are our two scenarios using the critical value method. Are we in the rejection region or are we not in the rejection region? And now we don't know what to do with that information yet, but we will. Certainly by the end of this chapter, we'll know what to do with that. All right. So for this example, we are given that alpha is 0.05, pardon me. So 5% is our alpha. And they say that our test statistic is equals 2, and we're testing a claim here. So let's set this up properly. So H naught is going to be that P is equal to 0.5. The alternative is that P is bigger than 0.5. Now, remember, a greater than means that it is a right tail. Oops. So let's set our alpha. This is C. Our alpha is a right tail because it's greater than, yeah. So we're here. They tell us that this is 5%. And I'm going to find the critical value by doing inverse norm, meaning the value that's on the z-axis. Inverse norm of 1 minus 0.05. Remember, inverse norm only knows area to the left. Inverse norm is the third one down. 1 minus 0.05. So this is 1.6449. And they tell us that the test statistic in this case is at 2, which means we are over here. So this is at z equals 2. And you can see my test statistic is definitely in the rejection region. All right, let's keep going. All right, so let's do our null hypothesis. Oops. And so let's draw our picture again. This is less than, so our alpha is going to be over here. Because it's a left tail. And this area here is 0.05. Our critical value is going to be inverse norm. And this is just 0.05. Because again, it's area to the left. And this gives us negative 1.6449 on the left side. So the one is positive, the one above is positive. This one is negative. And now we are going to have a not equal to. So our null hypothesis is that P is equal to 0.25. P is now not equal to 0.25. All right. And the not equal to means that we are actually having to split our alpha, which is 0.05, you see up there at the top. We have to split that up into two pieces. So half of 5% is 2.5%. And to get the critical values, I need to do inverse norm. 0.025. And let's see what we get. So this is negative 1.9600. There we are with our critical values. Now let's compare real quick. Oh, you know what I didn't do on the previous one was when Z was -3, that's way over here. We're definitely in the rejection region there. However, for this one, our test statistic is not in the rejection region. -1.23. So for the first two, we are in the rejection region, and for the last one here, we are not in the rejection region. Again, we're just about to find out what the significance of that is. Step 4, we're going to make a decision. We are either going to reject the null hypothesis, or we're going to fail to reject the null hypothesis. Those are our two conclusions that we're going to come to. If we reject the null hypothesis, then we're getting rid of the null hypothesis and we're going with the alternative hypothesis. If we fail to reject the null hypothesis, then we're sticking with the null hypothesis, whatever it was. And here is our interpretation. If the p-value is less than the alpha, then we reject the null hypothesis. If the p-value is bigger than alpha, then we fail to reject. The null hypothesis. That's the p-value method. The critical value method is if the test statistic is in the rejection region, then it's reject the null hypothesis. If it's not in the critical region, then we fail to reject. The null hypothesis. Now, you may want to highlight this and because you're going to refer back to this for the rest of the semester. Because both of these are whichever method you want to do, they should always jive with one another. And that's why I'm going to do both methods every time so that we can see that both statements will always be the same. All right. So let's keep going. If the claim is the alternative hypothesis, oh no. So I tried to make it so that the claim is always the claim is always the alternative hypothesis. And we're not going to worry about that wording for now. We are going to just end with reject or fail to reject the null hypothesis. All right, so the original claim, so our alpha is at 5%. Our null hypothesis is that the percent of M&Ms is greater than 5%. So this is a proportion. The alternative is P is bigger than 5%. All right, and it says the hypothesis test results in the p-value. So the p-value, now let's do this. Let's color code it a little bit. That is definitely less than our alpha. Alpha in this case is the 0.05. So 0.001 is less than that. So we go back to our, what if the p-value is less than the rejection region? Then we reject the null hypothesis, reject. Meaning we're not going to assume that the proportion is still 5%. We think that it's now bigger than 5% because we're rejecting the null hypothesis. All right. Original claim, women have heights with a mean not equal to 160 centimeters. So let's write down our null hypothesis. So mean is 160. The alternative is that it's not equal to. The p-value in this case is 0.0614. And that is definitely bigger than our alpha. I'm going to color code this properly. Let's see this. Definitely bigger than our alpha, which is 0.005. There. Which means we're going to fail to reject the null hypothesis. Meaning we are sticking with the mean height is 160 centimeters. We still think that it is, based on this p-value. All right. Now, in these tests, we need to keep in mind that there are ways for mistakes to creep in. A type 1 error, which is often referred to as an alpha error, is rejecting the null hypothesis when you should not have. So that's the equivalent of, so let's take a court case. The assumption, the null hypothesis is that the person is innocent. The alternative hypothesis is that the person is guilty, that the person has committed a crime, and we're going to test whether the person is guilty or not guilty. So by rejecting the null hypothesis when you should not have means that you found the person guilty when they actually did not commit the crime. So that is definitely an error. That's a mistake. The other type of error is you did the crime, but you were found not guilty. That's still a mistake. Now, the worst of those two errors, obviously, is the first one. But these are just the type of errors that can creep in, which is why you have to do a lot of different testing as we do this. And that's going to end the first part of this. There are, I think, 4 more parts that we'll need to keep an eye on as we're doing this. And so I will see you in the next video. Hang in there.